Welcome back, chemistry fans. Going to try and do the warm-up that we did in class today. It's going to cover a lot of topics dealing with Lewis structure, shapes, molecules, polarity, all that kind of stuff. So let's jump right into it here. And what you're going to see is that it asks first for a name of this Si2 molecule. Well, you're going to have to realize S and I are both over here on the right-hand side of your periodic table, meaning they're both nonmetals. This is covalent, meaning that we have to use prefixes. So you could call this monosulfur diiodide or diiodine, however you want to iodide, however you want to say that. You don't even have to have the mono if you don't want it. It could just be sulfur diiodide or diiodide, however you want to go about the naming. Lewis structure. Now, I do know that my structure is going to be single bonded I's to the S because they are halogens. However, I want to show my work. 1 minus half. My ones, they are each 8. That's 3 times 8 is 24. My half is 6 plus 14, and that's 20. That means there's a difference of 4. Divide that by 2, and you get 2, which is what I have here for my bond. So that's my Lewis structure. Now, my shape, because there are extra electrons, I need to make sure that there is a stable octet around this sulfur. And I also need to fill in my extra electrons, proving that the 20 electrons that I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 all come from what you were provided from the valence electrons originally. Now, because of these extra electrons sitting around the center atom, this is going to cause the molecule to bend. It is not going to cause it to cancel each other out because there's one on top, one on bottom. That's just an author's preference of where you can put them. You can put them both on top and reference then that they're all being pushed down, but reality is they will push downward and then outward towards you in a three-dimensional world. So this is a bent molecule, is its shape. Now the dipole on this one, we need to see what the size is. Iodines are much bigger than the sulfur is because they are on 2 energy levels below. Because of this fact, what we have is a difference in the way in which they will share electrons, which means that there is going to be a dipole moment. It also is because there's a bent molecule. So what we probably have is a positive side to this molecule and a negative side to this molecule. And what you have then is positive on top and negative on bottom. All right, ionic character. Ionic character is the difference between the two values from this electronegativity chart. So 2.66 minus 2.58, and that's 0.08. Well, once you have that difference, you got to put it on a classification scale of 0 to 0.4, and that would be something that is nonpolar or covalent, and then 0.4 up to 2, I believe, is what we have in the notes. Let me verify what those notes actually state so that I am consistent here. So in the notes, we have 2.0. That is correct. So 0.4 to 2.0, and that is going to be polar covalent. And then if we are greater than 2.0, what you have is something that is ionic or it is polar, however you want to phrase those. We have something that is much, much smaller. It's less than 0.1, it's 0.08. So that means that we have something that's actually non-polar covalent bonding. They're very, very similar in how they're going to share their electrons. Even though there is a vast difference in the size, I don't know what is the rationale why there is such a subtle difference between them. They both want electrons, I suppose, is all that this amounts to. Okay, so with that said, last detail in here is the overall polarity. How are you going to phrase this? Is this a polar molecule? Well, we have size that says it is polar. We have shape that says it is polar. Now we have non-polar bonds, but it's any one of those 3 factors is what is going to cause you to be polar. Okay, so that's everything that I wish to share with you from the warm-up today. Thank you very much. Talk to you again soon. Farewell. Bye-bye.